Yep, that's great. Thanks.
Okay, so first of all, good morning to everyone, and I'm Vaikunth as part of the Anna University research team here in Chennai, India, and we are very happy to be presenting our research project on the topic of optimizing helmet detection with hybrid YOLO models. So we'll be talking everything from the whys, the whats, and how we have done it. Apart from this, we'll also be discussing the results and discussions and what this holds for the future. So as this has been established, we can go on to the next slide, which is the what. So as the topic of the research paper states, the problem statement is one of a helmet detection. Now, helmet detection translates to an object detection problem statement. So in past literatures, several models that have been used for object detection include YOLO, convolution neural networks, SGD, and other networks. But YOLO is the most popular and the most efficient as proved, and so we have used it. But we have added a slight twist to YOLO. Now, what this twist is adding a pre-CNN that feeds features to the YOLO model. Now, these models and the independent YOLO models have been compared, and that's why we can see here that a comparison of six models has been done to find the best in categories of accuracy, detection speed, and overall. So these six models are YOLO V8, YOLO V9, YOLO V11, and the corresponding hybridized models, which will be called as h-YOLO in this presentation. Next, we'll be discussing the why. So I think it's very important to understand why we have done this project, as every project will have its motivation. And I think a project of helmet detection should be quite obvious. But here are some statistics to reinstate the fact that helmets are very important in road traffic dynamics. So one of the statistics from National Highway Traffic Safety Administration India states that 37% of effectiveness has been increased by reducing the fatal injuries for motorcycle operators and 41% effective for motorcycle passengers. Apart from this, for those who ride bikes, helmets provide up to 63 or 88% risk reduction from head, brain, or severe injury from all ages of bicyclists. Now, since we know that helmets are very important, next we can say that an efficient system for detecting helmets and if whether riders in a traffic scenario are wearing helmets or not has to be established. So, in this world of rising use of machine learning and other predictive models, we are trying to revolutionize this helmet detection avenue by introducing our way of predicting this. So, if this has been implemented properly, the fatalities and risk of injury will be reduced much. Apart from this, the main topic of this is using machine learning to aid helmet detection. So now we can go on to the steps of the training model. But before going on to the steps of the training model, I will be discussing about the dataset collection, which is basically a custom data set that our team of researchers have gathered and sourced by taking photos of traffic scenarios here in India and adding this to a ready-made data set that was available in roboflow.com. Now, this data set is raw and hence has to be uh, pre-processed before any model training can happen. Hence, pre-processing techniques such as pixel normalization, image augmentation, etc., will be performed to curate the dataset to our requirements. Next, the actual model training of the YOLO and the h-YOLO models, including the steps of hyperparameters, will be discussed. And for this, we have our co-author here, Balamurali S, to discuss this. I'll be handing it over, so please bear with me.
Uh, uh, can you hear me, right?
Yep, we can hear you. Thanks.
Yeah. Good morning to all the people present in the currently present in the meeting. As my teammate Vaikunth established the what's and whys of the complete project, so I will be here discussing about the all the neural networks and type of neural network and technical side of the project that we have done. Initially, we'll start by uh, I initially start by explaining the individual components, such as individual component of the project that we use, such as CNNs, YOLO, and YOLOs. And next we'll be, and then I will be explaining about the hybrid YOLO model that we used. First is we understand what is CNN. So CNN is the essential tool in computer vision, which is used for tasks like image classification, object detection, and segmentations. What makes CNN so powerful is that it is ability to extract patterns such as edges, textures, or shapes directly from the images. Because of these advantages, it is mainly used in autonomous vehicles and medical imaging. So next is, what do you mean by convolution? Convolution is the heart of CNN process. Here there's a small matrix called as filter or kernel slides over an image that is used to create a feature map. This feature map detect patterns. For instance, one filter map can identify vertical edges and another one can focus on textures. For example, let's consider the case of a hummingbird, which is an example that we'll be using all throughout this explanation of these technical networks. Uh, One kernel might detect the sharp edges of the beak, whereas other might highlight the texture of its features. This process enables the CNN to focus on relevant details while ignoring the background. So next, and then in the next slide, we'll be discussing more. We'll be discussing about the activation. So in CNN, there are many activation methods, but in CNN we'll be using ReLU activation methods, which translates to rectifier linear unit. It adds a non-linearity to the model by setting negative values to 0 and keeping the positive ones unchanged. But why it is so important, at least in CNN? Because then only network could only learn the linear patterns. By introducing non-linearity, CNN can identify the complex interactions in the data. Next is a batch normalization. Batch normalization is which helps stabilize the training by normalizing of feature values. This ensures that consistency is valued across all the layers and faster convergence and reduced overfitting. And next we'll be telling this is simple image of a simple CNN architecture. Here we have an example of hummingbird and also all the layers that we have. So initially, for consider case that is given here. Next is, yeah, like there's a given here. Here it consists of input layer, hidden layers, and also output layers. Input layer takes the image as a matrix of pixel values. Each pixel intensity is represented numerically, which is followed by hidden layers. Hidden layers is the main layer of this whole CNN network. It is where the patterns are detected. Early layers find basic features like edges, while deeper layers identify complex patterns like birds' feathers or beak, etc. Next is the output layer. The output layer assigns probabilities to categories like bird, cat, or dog. Since in this case it belongs to a bird, so it will give the output as a bird for accurate classification. Next, this image tells about a image to metric conversion. Image to metric conversion. So here, this process how it goes is that first initially the image is divided into grid of pixels with each pixel value representing its brightness or color intensities, and these values form a matrix which becomes CNN's input. This CNN process is passed through convolution, ReLU, batch normalization, and it is used for extracting meaningful patterns. And this is the exam. This is a image that we use. This is structure that we use for doing this project. It consists of input. Which is of 28 into 28 pixel grid. Next is convolution. Next is a convolution. Filters slide over the image, return features like edges or textures. For example, one filter might highlight the bird wings and etc. Next, we'll go to doing the batch normalization. It ensures that all the features are consistent and the stability is improved. Next is followed by activation. It filters the irrelevant details, like irrelevant and focus on key features. Next is output. Output is in the refined feature maps. So till now, I have been discussing about individual component of CNNs. Now I will be discussing more about another individual component, another individual neural network called as YOLO. YOLO will translate to you only look once. It's a real-time object detection system. Unlike traditional systems that separates region, selection, and classification, YOLO processes everything at once, making it more fast as well as efficient. How it actually works. When an image is fed into YOLO, it divides the image into grid. Each grid cell predicts bounding boxes and conference codes. For example, consider for biker, which is a common example that you're going to use throughout all the project. As a biker, YOLO can detect the rider and helmet simultaneously by creating boxes around them. Why it is mainly used over any other neural networks is that it can detect multiple objects at once, making it ideal for tasks like surveillance and autonomous driving. So this slide will tell about the this slide will tell about the working of the hybrid model. Hybrid model is the hybrid model is the model that we use for computer for this project. So it starts with so what does hybrid model actually mean? So it actually means integrating YOLO with addition techniques for better accuracy. This ensures that reliable element detection is formed even in the complex scenarios. So how it actually works? Firstly, YOLO identifies potential element regions, and non-maximum suppression filters, called as NMS, are produced. With the help of this NMS, it makes sure that only the most accurate ones are present. And for challenging cases like low visibility or low visibility, the model uses contextual information for better direction. And what are advantages of using a hybrid model over individual model is that it balances speed as well as accuracy, making it ideal for real world scenarios. And this is a simple pipeline diagram that we pipeline. This is a simple pipeline diagram which we used for this project. And how it goes? It goes by it has different layers: input layer, pre-processing layer, and splitting layer, and hybridization block, which will be followed by the content direction model. So we'll explain this. We'll explain this with the scenario that we used for this project, that is helmet detection. So here input data consists of raw data, which includes all images, which is a mixture of both images that we took from the traffic signals here in India, and also some of the some of the images that we took directly from the internet also. So here input data will collect. It's all about collecting all the data. Next, will followed by pre-processing. So in pre-processing, there are three main techniques: cleaning, augmentation, and resizing. So cleaning means that it removes irrelevant features and all the noises which are present in the images. And augmentation is that adding variety, such as by adding or flipping it, adjusting the brightness, and making a model more robust to the scenarios. Next is resizing it, reducing the standardizing image into 24 into 20, 224 into 224 pixels. It will be followed by splitting the data. Here, data are split into three methods: test into testing, training, and validation. So according to this, we have split in such a way that 5% goes for testing, 80% goes for training, and 15% goes to the uh, 15% goes to the validation. Next is the model training. Model training here is done by hybridization block. Here in this architecture, hybridization block is the most important process. So it involves 1 minute, sorry. So it involves hyperparameter configuration, that is tuning the parameters like learning rate, batch size, and increasing number of epochs as per to get the best performance. And testing the multiple CNN models. So we test between all of the CNN models, the CNN 1, 2, and 3, and followed by the YOLO models. And next, integrating all the CNN model into YOLO model into YOLO models. Next is validation result. Uh, YOLO models will be sent for a final testing. Next will be validating the results. This validation bit, this amount of email that we keep for using in validation data is used, and also the help of the hybridization block that we did, we able to refine the model during the training. And after selecting the best performing model, testing ensure and we make sure after we set the best performing model, ensure that there the model is able to find give results for all the possible data in all different conditions. And next is final detection of the output. The final trained model will give an output where to and give the bounding give along with the bounding boxes whether the given image as a person who is wearing helmet or not. So these are technical aspects of this whole project that we did. Now my teammate Vaikunth will tell about the matrices that we follow and also the results that we got by implementing all these networks, and also what are the future avenues available for this project. So I'll pass this to him.
Okay, so thank you so much, Bala, for filling us in on the details and technical aspects of this project. Now I'll be moving on to the results and what this holds for the future. But before moving on to the results, I think it's important to know what metrics we have used to assess each of these models. So let me go over that. First is precision. Precision and recall, both of these are quite famous classification and detection metrics that are used in traces. What precision means is the correctness of the result. So, how many of the positives detected are actually true positives? And now, when we're talking about recall, recall refers to the number of true positives that are detected out of all the overall positives that are present in the data set. But the thing is, what we usually find is that if we try to increase precision, then recall reduces. And when we try to increase recall, precision reduces. One cannot simultaneously try to see improvement in both of these metrics. And because of this, we tend to use other models that give an overall performance indication, one of which is F1 score. But here we have used mean average precision at an IOU threshold of zero point 0.5. And apart from performance accuracy testing, we also measure these models in terms of the times taken, the times which are training times, which is the time taken by the model to take all the images, process it, train it through the 50 epochs that we have set it for, and give the model hyperparameters and the weights. Next is the testing time, which refers to inference time in this case, ignoring both the pre-processing and the post-processing time that is done before the inference, since inference time is the actual time that varies between each of these models. Now, as we got an overview of the metrics that have been used, we can move on to the results. So, when we compare the plain YOLO models and the hybridized YOLO models, we find that the hybridized YOLO models are better in terms of accuracy. And this is to be expected since we have added extra components which are pre-CNNs that feeds features into the hybrid YOLO models. But in terms of speed alone, plain YOLO models are superior. This is because plain YOLO models are lacking the extra component that has been used in the h-YOLO models. And in terms of the accuracy that I've been talking about for h-YOLO models, they see an improvement of about 2 to 3% in the MAP score. And 2 to 3% is quite a significant amount in accuracy for h-YOLO models. And this is because 2 to 3% in a heavily dense traffic scenario can mean that it can detect a lot more number of riders who are wearing helmets or not wearing helmets. So here we have a table that compares each of these models in terms of MAP score and the testing time. So before analyzing this table, we should be aware of one thing, which is that as it might sound, YOLO V11 is the latest model that has been come from the YOLO development team, and they boast the fastest training and testing times. As we can see from a graph here that has been taken from the Ultralytics website, which shows the dark blue line, which represents YOLO V11, and we can clearly see that it ranges for around 10 to 12 milliseconds, which is much faster than the other models. Since that has been established, which is the fact that YOLO V11 models are the fastest among the bunch, we can now talk about the best in terms of MAP score alone and the testing times. So if you look at MAP alone, the highest is given by the h-YOLO V9 models, which is 93.2%, while the testing time, the shortest is given by the plain YOLO V11 models of 10.1 milliseconds. But it is important to see these models and compare them not only in terms of individual performance metrics, but also as an overall and a holistic view. So, if we do that, we will come to know that h-YOLO V11 models with an MAP score of 91.4 percentage and a testing time of 11.9 milliseconds performs best overall, and that is what has been shown here. The fastest model is YOLO V11. The best MAP is given by h-YOLO V9. But if we want a good balance between MAP and the testing time, we should go for h-YOLO V11. Okay, so let me recap or summarize what we have presented so far. Firstly, a data set that has been formed using custom images and ready-made images from the internet has been pre-processed and fed into the pre-CNN, which is part of the entire hybridized YOLO pipeline. The pre-CNN's feed features to the YOLO models. Here three of them, YOLO V8, V9, V11, and the results are compared with the plain YOLO models of YOLO V8, V9, and V11. And we see that the hybrid models perform significantly better on than their non-hybrid counterparts, outperforming them by 2 to 3%. Within the hybrid YOLO models, the h-YOLO V9 is found to have the highest accuracy, followed by the V11. In terms of training and testing times, though, the V11 beats the V9. Therefore, in conclusion, we arrive that in middle ground, h-YOLO V11 models are the best overall. Since we have noted this, we can talk about the future avenues of exploration. This project can translate easily into a license plate identification project. What this means is that first, the cameras that are fixed onto traffic lights will analyze the traffic scenario in junctions or stoplights, and then detect if helmets are worn by the riders or not. And if these helmets are not been worn, then the license plate of that particular rider can be identified and sent to the law enforcement agency, who then can do their job. Apart from this, we can also extend this to other safety sites and places where safety compliance is critical. For example, construction sites where helmet wearing is very crucial. So this is a form of transfer learning. Since our model has already been trained on bike and motorbike helmets, transferring this knowledge onto construction helmets will probably give a high accuracy. Apart from this, our model will also be good for other safety equipment detection such as gloves and boots. So now we are concluding the presentation by saying that in an increasingly motorized environment, it is important to follow all the safety measures to a T. And our efficient helmet detection system is aimed at achieving this goal. And the highlight of this project is that we have found that our hybridized YOLO V11 model proves to be the best model that provides a good balance between both the overall accuracy or MAP score and the inference time taken. Thank you.